first, yeah. So first, I realized that people might have few doubts regarding last lecture. So I just wanted to revisit them. So like people have been asking me about that. So and they were really great doubts. And so first of all, whenever like I'm teaching and you feel like you don't understand something, uh, rather than waiting to understand it yourself, it's completely fine if you can just ping me on if you can just directly send a message on Zoom chat or anything, and yeah, I'll revisit the stuff again. Um, first of all, while so, mm, so people had some doubts in this derivation. So in training, what we are trying to do is yeah. So, uh, so we have X train and Y train. We are trying to estimate theta here, and then given X test and this theta, we want Y test. So this is our goal. Yeah. So in training, our goal is to obtain this, and in testing, our goal is to obtain this. So yeah, as mentioned in training, we want a probability of theta given X train and Y train. So that's what we are after. And whenever you see conditional probabilities, one way to the one thing that helps me is if you see a formula like this, then just discard everything that's on the that's already given, that is constant throughout the equation. So I'll give you example of that in testing, but so here I'm just applying a simple bias rule where probability of and yeah, so consider this X train Y train as some variable uh, t, then probability of theta given t would be just probability of t given theta times probability of theta divided by probability of t. So this t is just probability of X train Y train, and then this p of t, I'm breaking it down since, as I said, is probability of X train Y train, and then I'm again yeah breaking it down, probability of X train given Y train times probability of Y train. So I hope this step is clear. Um, yeah, okay. Yeah, I wanted to break this down as probability of Y train given X train, and you can see that both of these are equal, right? So probability of X train Y train is equals to probability of X train given Y train times probability of Y train, and this is same as probability of Y train given X train times probability of X train. Yeah, I hope you know this. Then once I break it down it in this way, and I'm also again breaking this down. So now, so when I'm breaking this down, assume that theta is already given to you. So this should be given theta. So yeah, if you can see when I'm breaking this down into this part, so if theta is already given to me in all the three equation, yeah, in the right part, then you can just discard it, discard it for in the sense to understand it. So this is just some information that is given to you, and yeah, so it could be anything here, and it wouldn't matter. All the formulas of probability that you know would still hold. So this probability of x train y train is the, yeah. So probability of x train times probability of y train given x train, and in all the three probabilities, theta is some information that I've already been given. And then what I want to do is probability of x train given theta is same as probability of x train, because x train is the variable, the data that is already provided to you. So this and this got cancelled out, and then what you would have been left with is this. And that's where this equation came in. And for testing again, what I wanted to do is, now this information is given, and even this information is given in the right hand side of the equation as well, so you can like uh, yeah, so all the formulae of probability would still hold. So it's just assume that this part is not given initially and this part is not given initially. Then you can see that this makes sense, right? And then you can just write down there is some information that is already given to you. And yeah, in all of the probability formulae, this will hold. If probability of a is equals to sigma probability of a comma b b, uh, then now I can just put in all the information that I might have x y z, and then I can again put in all the information that I might have x y z. So I hope this step is clear.
Um, one one question.
Hmm?
So before that, can you scroll up to the testing objective?
Yeah,
Yeah. So here the testing objective is given y test. We are trying to get y test given x test, s test, x train and y train.
yeah,
And here we don't have theta in the given parameters, right?
yeah. We don't. So we are putting theta into the picture by marginalizing out uh, y test.
Okay. Because before, initially, when you introduced testing and training, you had theta in the given also. So that what was confusing me.
So
Yeah.
here,
Yeah.
yeah. So here, what I wanted to try to say is, so you are building it from the ground up, right? So we had just showed these three variables right now, like
Okay.
that is given to us, and then yeah. So for training, we are obtaining this part, and for testing, we would use this and this, but this would be obtained again from this.
Okay. Got it.
If you scroll up, I think you did mention theta somewhere. Just scroll up.
Yeah.
Yeah, up. Keep going up.
Hmm?
Yeah, just here. You know,
Oh, yeah,
testing. We don't need theta here, right?
yeah. I'm sorry. Yeah, this is-
Oh, yeah, that makes sense. Thank you.
yeah. So yeah, once we marginalized out this, then this is what we get. So this is just here theta getting marginalized out. And then again, I'm trying to break this equation using Bayes rule. Uh, Now, as I said, you can again, whatever that's given to you can just, if something is given in the left side of the equation and even in the side of the equation, you can just safely discard it. So here, the way I'm breaking it down is, yeah, wait a second. Mm, yeah, so I just want to break this down as probability of yt as given theta into probability of theta. This is something that I'm already being given. So here I should also have y train in here. So these are the three variables that's given, and now I break it down, and then now I also have theta. These are the four variables, and yeah, again theta. These three variables are already given to me. So now But as I mentioned, y-test is only dependent on theta and x-test. You wouldn't want to use your training set for getting the y-test. So you can remove x-train and y-train from this, and you
I've got a question. Sorry,
yeah.
I didn't get it. Like from the equation of marginalization, how did you break it down to that? So I understand like this equation where you said probability of y test given all this x
Hmm.
test y train etc. and equal to that to this integration where we marginalize out the theta.
Hmm.
After that, I didn't get it. How did you get that equation? Like like properties of probability are you applying?
Yeah. What I'm doing is just probability of a given b is probability of uh, a and b is probability of a given b into probability of b. Now here b is my theta and a is my y test. And now, as I said, you can just put in any number of variables that you have here, x, y, z. Then this would still hold, given that, uh, yeah, so probability of A and B. Now, there might be something here. Then you can just put the same stuff again here, and the same stuff can again go here. So all the formulas of probability will still hold if you just, yeah, just give, if you kind of do, yeah, if in all the probabilities you have already some information about it. So this thing is still valid. It's just some information that you have, but you are not breaking down that information. So this was. And now this dash is just this x test, x train and y train. So now it's like probability of yts given theta. And now I need to put in all of this stuff. Then this is x test, x train, and y train, and times probability of theta. This b is theta, and now again I have to put in all of this stuff, which is x test, x train. Does that make sense?
Yeah, it makes sense. Thank you.
Yeah. So now, as I said, given your test set, you don't need this. Yeah, you don't need to predict your test outcome using your training data. You just need to predict it using x test and theta. So yeah, so y test should only be dependent on theta and x test. So what we do is yeah, so it should be independent of x train and y train. So you discard these and this random variables, and similarly, you only need to guess your theta using x train and y train. You don't need your test set. So and that's how we come up on here, and like this is the same as this, and yeah, and then this is just rewriting this equation. So any doubts about these two proofs? Okay, I'm hoping not. And yeah, please feel free to ask it again. Yeah, I'm going to go through it again one more time if you want it. And the other doubt, like people asked me, was the intuition for why the mean should be this W transpose X. Uh, so yeah, aim for starting this this last example was we wanted to do linear regression, right? And yeah, so and we have made this prediction that new one is W transpose X. And this is a prediction saying that basically we, since we wanted to do linear regression, there y is centered around this linear line, and this is x, and this is y, and yeah, so linearity in x is just linear equation. So this is dot product of w and x, which is w transpose x. So that's why the mean of we are assuming that this mean of y would be centered around a linear line, which is given by w transpose x. So any further doubts in the last lecture?
Yeah, I had some doubts regarding the notation of multivariate normal. Can you scroll up to that? I
Yeah,
was just revisiting those notes before this call.
yeah. Just tell me where to stop.
Yeah. Here. So here you said that the capital X is a multivariate random variable, right? And it
Yeah,
is as so we are basically stacking n univariate variables, which are these cursive x's.
yeah,
And so when you say that p of x is the equation of probability, so that is probability of uh, that
this
is a multivariate random variable, and it is that is the joint probability of all the univariate random variables,
yeah.
or is that the data point?
um so this is giving you a PDF, and so
No. I'm talking about the equation before. Probability of x is joint of probability of x1, x2, xn.
yeah, okay, oh yeah. So this is giving me, yeah, the probability of the data point, but like, so the way you can interpret this is uh, x1 is 1, x2 is 3, and let's say we have a multivariate random variable with 3 dimensions. So what you are interested, okay, let's keep it to 2, 1 and 3. So what you are interested in is in some probability at x1 is 1 and y3 is 3. So yeah, so this would give me the value of PDF at kind of this point, if you can assume a bowl like structure here. And yeah,
Okay.
so and then what this basically is, it's kind of both of these things. It's probability of that data point, which you can also say it's the probability of the x1 variable is 1 and x2 variable is 3. So you can kind of say it's also joint probability. And
Of
yeah,
all the, so we can say that this is the joint probability of all the univariate random variables to give the probability of the multivariate random variable.
yeah, correct.
And so, okay, so going below, when we write normal distribution of x is equal to x, so that realization capital X is equal to small x, so that small x is a multivariate random variable, right? It is a vector.
Yeah, a vector of random variables.
Okay, cool.
Okay,
Thank
nice.
you.
Any other doubts about the lecture?
Regarding mean, when we take W transpose X as mean, I still don't get it. Why we take that as a mean? I mean, I understand that's like a kind of a fine combination of the input variable, but why are we taking that as a mean?
Yeah, so because so, yeah, you only answer me. What do we want while doing linear regression? Oh, yeah, what is our goal? End goal?
I mean, we're trying to like minimize the error function, right? So we're trying to minimize the sum of square error.
Yeah, but we are imposing this. That's correct. But we while doing a linear regression, what we are imposing on is that y should be a linear function of x, right? Like y is distributed. Like, what we are trying to estimate is this kind of a linear line that is like linear with respect to the linear with respect to our weights, and then this x is our feature vector. uh, while doing linear regression, we itself are interested in this quantity, w1 x1 plus w2 x2. And so, uh, So in order to do this, we are kind of we are assuming that why is this yeah, if you're part of a Shalizi said in this starting lecture, she said that uh, we can always write y as and this epsilon is some noise. Now generally this noise won't be independent of x, but for doing the linear regression, a good weight vector would only happen when this we would assume this noise to be Gaussian and yeah, and basically independent of x. So because uh, yeah, and this thing is exactly same as this equation. If I'm assuming univariate noise, sorry, uniform noise, then yeah, these both are exactly same. The assumption that we are making here is that y can be written down in such a form, and we are interested in finding the k because basically we are doing a linear regression. Does that answer your question?
Somehow. So, I mean, when we take a mean, we divide it by the number of data point we have. But here we are not dividing it by that. We're just taking the combination of the data point, like the weighted combination, I would say.
Yeah. So what you are assuming here, y is this? So if let's say now our assumption is I am just if these are the data points that are given. Now I'm assuming there is this all these data points that are given to me. If I take a mean of this, I will get a line passing through all of them, and all of these noise would be independent of the position of x, and it would be just be sampled from a uniform Gaussian. So and and, and this is our like this is what simply linear regression is, right? We want to define a line that is yeah, we are assuming that y should come from this, and uh, so yeah, assuming that y is the mean of this random variable y is that line, we are yeah, we are incorporating our assumptions.
Yeah, but when we take mean, we divide by the number of data point, right? So why are we not dividing by the number of data point?
Yeah, so now we are dealing with random variables. So a data point is nothing but just a sample. Now, whenever a data point is given to you, just assume it the data point is just a sample of a random variable. Like this. So yeah, in order to get a data point, you would just sample x and you would just sample y, and then maybe you get this data point. But now since we are dealing with random variables and probability distribution, we don't need to explicitly say how much data points we have. What we are just defining is the structure of that probability distribution.
Right, okay.
Yeah. So, uh, any other doubt? I hope that was clear to you.
Yeah, that's helpful. Thank you.
Yeah. Any other doubts? Okay. So I think now we'll move on to the review two, the second review. So what last week what we did was yeah, so we started out with why Bayesian perspective is useful, in what way it helps us. Then we had a talk on uh, frequentist versus Bayesian approach. Then we started out how one goes ahead doing analysis, doing training and testing using uh, yeah, in a Bayesian way. And then we went over some specifics of multivariate normal, and then we ended up with an example of doing linear regression in a Bayesian perspective. So uh, that linear regression in the Bayesian perspective was one of the three forms in which we can do analysis with Bayesian inference. So yeah. So at the end, what you are interested in is getting your. Mm, I will. I'm writing down that same training equation once again. What we are interested in. Give me a minute, yeah. Yeah. So we are in all of these. What we are interested in is finding a parameters theta that kind of best fit our model. And there are kind of two ways to think about it. I like to go through both the ways. Mm, I just wanted to copy this equation. Yeah. So so we are just interested in all of estimating this. And now while doing this, uh, so, and if depending on which quantities we focus on, uh, I'll explain all of these three to you. We can define three kinds of estimates: MLE, MEP, and Bayesian. So probability of theta given extreme and right. Yeah. So if uh, if we are interested in this, and what we want to do is maximize, yeah, this thing is called a prior, and this we can call as likelihood. Why likelihood? I'll say that in a minute. And this is nothing but a maximum likelihood estimate. Maximum. Yeah. So we are interested in uh, these three quantities, and what you will see is if we just estimate this, this would be our MLE estimate. This would be our MAP estimate. And uh, I would go through this in a minute. Why these are these, and this entire thing would be a Bayesian. So yeah, depending on yeah, if ML is the simplest estimate, we would add yeah, and adding complexities to it, we would kind of move forward. So coming from this, this is one kind of way to define it, and other might be. So let's say you have few, these are some of the data points that you have been given, and you want to evaluate. Let's say I'm giving you a task of each of one to define a probability distribution from which this data came from. So you are just seeing these samples of some distribution, but you don't know which distribution these data points come from. And I give each of you some, I give you each of one the task of give me a probability distribution that you think these data points come from. So let's say one of you might say, yeah, one of you come up with, let's say this is -5, this is +5, and this is, let's remove this, keep it, and this is 0. So one of you might say, let's say this comes from uniform from -5 to 5. Uh, some other one would say this comes from normal distribution centered around 0, with standard deviation of 2. The third person would say normal distribution centered around 0 with standard deviation of 10. So how would I be able to evaluate your distributions on this data? So yeah, so one of my tasks would be to so it could come from this distribution, right? Like it's not impossible that I can see that uniform wouldn't be able to generate this kind of data points. So in order to, yeah, tell me which probability distribution is better, one of the one of the ways that we can evaluate the distribution is using this MLE estimate. What MLE tells you is, given this distribution, given a distribution P of X, how likely are you to observe the X? Now, this data points, I would call it, let's XD. So, given given some distribution on X, how likely would I be able to see these data points? And one of the major assumptions that we'll make here is all of these data points are IID. And again, this is not that hard to get, right? Because most of these data, samples of a distribution are independent of the previous samples. So, say if I want to sample from a uniform distribution in 0 to 1, uh, my second sample wouldn't be dependent on the first sample. So yeah, so if all of so uh, s- let's say this is x1, x2, and this is xn. So I have n data points. I have some p of x distribution given to me, and what I want to evaluate is joint probability, the probability of yeah. So uh, yeah, so probability of x is x1. um, yeah, and basically a joint probability that x can be all of these. And now what I'm, as I said, each of these data points is independent of each other. What I can say is yeah, so what I want to evaluate is that x gets the value of x1 and x also gets the value of x2 and x also gets the value of till xn. But since all of these are independent of each other, I can just focus on each of them individually and see what's the probability of me seeing this data point, this data point, this data point under all the distributions. And yeah, and this is how I would evaluate my yeah, evaluate each of these distributions at, let's say this is A, this is B, and this is C. And which one of these, and this is nothing but likelihood of seeing your data. And then which of these distribution is the best one, I would just select, let's say this is P of I. P of I indicates, uh, not P of I, P of J indicates the distribution. Then I would just pick the distribution which is the best one. Now, normally, yeah, so if we want, what we can do is for -5 to 5, yeah, can anyone tell me what would be the probability at each data point for from if uh, yeah, from uniformly -5 to 5? Hello.
Isn't that the probability would be same for all the data point because it's a uniform distribution?
Yeah, yeah, it would be same, but how would you calculate that constant?
Is it like 1 divided by the interval size? It's like giving equal weightage to all the data points.
Mm, sorry, what?
Like basically reciprocal of the range between the two values, like we are calculating the uniform distribution, like giving the equal weightage. I'm not sure, but yeah. Like
Yeah, yeah, but so for each data point using in this uniform, so what it would be the same across all the points, but what would be that constant?
okay,
Isn't that be one? Because
No.
all are no,
Would it be 1 by 10?
Yeah, correct, exactly.
right, okay.
So why? So if you want, the one of the way that you would do that is yeah, yeah, in its domain from -5 to 5, each of them would get a constant value c, and then yeah, just c, and then you need to integrate that, and this value should end up being 1. And so this is nothing but should be 1, and then this is nothing 10cx. Yeah, so 10c should be 1, and then c should be 1 by 10. So yeah, so each of these data point would get uh, I shouldn't say probability because it's a continuous function, but this quantity should be would be evaluated to 1 by 10 for each of the data points, and then we would end up at 1 by 10 raised to n. So this is the likelihood of my data under uniform distribution. Now, okay, another question. Can anyone tell me what is the likelihood of my data under uniform from um, -1 to 1? If these are the data points that I observed, this is -4, this is -3, this is 4. Yeah.
1 by 2 raised to n.
No. So it was kind of a tricky question because now,
it would be zero, right?
yeah, correct. So since there are these data points that lie outside the range of -1 to 1, so while doing this, phi of I is equals to 1 to n, p of jx is equals to xi. And now whenever if this is a uniform distribution, whenever x is something like -4, anything that's not lying within -1 to 1, it would be 0, and the entire likelihood would be 0. So yeah, and so similarly, you can calculate the likelihood for your normal distribution as well. And here this is mean and this is variance. Now, yeah, and generally, what we would want is the, the data comes from which distribution is kind of a hyperparameter, because so what you can do is you can just yeah, you can put in any of the distributions and see uh, how it's performing, but uh, we cannot tune our model to which distribution suits its best. But what we can tune is the parameters of those distribution. Like uh, we can say, okay, this thing comes from a normal distribution. Now, the choice of normal is a kind of hyperparameter where, yeah, there is no model that can give me which distribution it comes from. Like the only way I can get is like trying all the different distributions that I think it might come from. But yeah, once I pinpoint to a distribution, what I'm interested is in getting the parameters of this distribution, mean and variance. Now I can do my analysis on just knowing that, okay, this comes from normal distribution, and now which mean and which variance would provide me yeah, would provide me a maximum likelihood of seeing the data that was given to me. So then what it generally boils down is, now I have some distribution, and now what I'm interested in getting the parameters of those distribution. So uh, yeah, for normal, what I would be interested is in getting mean and variance, and even for beta, you would have two parameters, a comma b. So so normal of 0 2 would fit better here, or normal of 0 10, or say normal of 5 7. So I'm kind of interested in all of these quantities. And now the way I would go about is maximize over theta. This is the likelihood. Does that make sense? So what I'm doing is, this probability distribution is fixed. P of P, this is normal. This theta indicates my parameters of the distribution. So it's kind of saying, go through all the theta that I have. Uh, yeah, so all the possible values of theta. Assume that that particular value of theta that I have is given to me, and then this distribution would be defined using. People also write it like this way. So whenever you see these two quantities, assume that both of these are equivalent. So yeah, both of these says this probability distribution is parameterized by theta, and this is kind of conveying that you have those set of values of theta, and then you kind of estimate what is the probability of seeing this data, and then you go through all of the theta, and the one that maximizes this is your maximum likelihood estimate for that theta. And now, as I said, this is just the likelihood of data. Now, if I'm giving you this data points, that what we are interested in. This should be Does this much make sense? Any doubts still here? Yeah, like just a thumbs up or anything would be a good indicator of whether you are understanding and whether you are with me.
Just a quick question. If we taking it as a normal distribution, so the parameter would be either mean or variance, right? So what does theta actually indicate? Does it indicate all the parameters?
Yeah, all the parameters. So theta is not some 1D vector. Theta might be mean, like all the parameters that that distribution might have.
Okay, got it. Thank you.
Cool. Yeah. Any more questions? Okay. And this maximum likelihood of seen data is also sometimes written as a theta of x, where yeah, theta just indicates which parameter gives you the best likelihood of given this x data. Just kind of a notation of how likelihood is represented. And so now, once after doing this likelihood estimate, what will be end up is with again only the max of this theta. And now if you connect to the previous lectures, if theta had some this distribution, only thing we'll end up with this one. We still won't have any distribution that there is this point estimate of the theta that we would be getting, and that theta is basically the mode of the distribution. So yeah, so again, maximum likelihood estimate just gives you a point estimate, doesn't tell you anything else. And now if I connect to this part, what we are interested is in yeah, getting the maximum value of this quantity in the training part. And now if yeah, over like which theta would provide me the maximum value of this. Now this is independent of theta, and yeah, if you connect to my linear regression example, we would just discard this only in the maximum likelihood estimate. And now in the maximum likelihood estimate, we are also saying that we don't have any prior on theta. Like if here, if I'm saying that I'm interested in all the normal distributions, then what I'm saying, I don't have any information about the mean and the variance. It could be anything. So, so basically, the probability of connecting it to normal distribution. Here, I'm saying I don't have any information of the probability of saying which mean or probability of the variance. And in some use cases this makes sense that if you are just interested like all of the means that could possibly come are equally likely. And then if if we don't have these, what we are basically saying is since we don't have any information, we are just assuming that it's kind of a uniform distribution on all the possible values of theta. So even yeah, so even this thing doesn't come into the picture when getting this maximum thing over theta. And then what we are basically end up is getting the probability of y train given x train and theta. So for MLE, we are only concerned with this quantity. So 2 max over theta of this one. This is your this theta hat is would be your MLE estimate. This would be your likelihood of seeing your data points. Okay. Uh, is this all making sense to you? What we are doing in the maximum likelihood estimate? Any doubts still here? And if you want me to repeat something, if you want to take your time to process uh, what's been done, and if you want me to slow down Please indicate if I should continue. Then please show a thumbs up or just unmute yourself and say proceed. Hello. Yeah.
Yeah, I think it's clear. Like I had just one doubt in a way. So
Hmm?
in this case, let's say we whatever data like we are trying to identify the distribution of that data. So initially we start with like that particular mean, like the mean of the data that we have, and like we fine tune it, or how is it like in this hyperparameter search for theta?
Yeah. So we'll go through that. Sometimes you get directly a closed form solution of which theta would be the best, and sometimes you might need to do gradient descent or yeah.
Means,
So
but in a way,
hmm?
what I am asking is like what is the starting point in a way, like like should do we start with like assuming that like let's say like whatever the data having like a mean, so like that would only be the kind of actual true model parameter itself.
No, so like you are saying the starting point of this search, right, for theta.
Yeah, yeah, yeah.
Yeah. So that's what I'm saying. So we'll kind of go through that now, but it would what you would end up doing is sometimes you would get while solving this equation, what you get sometimes what you do get is a closed form solution, and if not, then what you can do is any of the optimization search methods you can just plug this to a gradient descent and start with a random theta, do a gradient descent, take derivative of this part quantity and find the optimal theta.
Okay.
And and one important aspect that you need to take care about is let's say when theta yeah again let's say P of the probability distribution was a multivariate normal, then you then this theta would be uh, uh, would be a mean vector and a covariance matrix. And if you are assuming that if you want to do the search on the covariance matrix, then theta should follow all the properties of covariance matrix. So it would be kind of a restrictive search where your covariance matrix cannot be anything. And can anyone tell me what are the two main properties of the covariance matrix that we went through in the last lecture?
It's
So it
like
has to be symmetric and positive semi-definite.
Yeah, true.
yeah.
So it would be a restricted search in the parameter space. You cannot just uh, naively plug into the gradient descent because it might come up with a value for the covariance matrix that wouldn't define a covariance matrix because it won't be symmetric or positive symmetric. That this one thing that you need to care about while doing this optimization.
Oh, isn't that's why we used EMR algorithm instead of the gradient descent or stochastic gradient descent?
Yeah, that's also one reason, and I don't want to introduce EM right now because we'll do that after latent after describing latent variable models. So yeah now okay, so what I wanted to do now is kind of relate this maximum likelihood estimate, all the machine learning that we have been doing till now. So MLE estimate, what I'm claiming is same as cross entropy estimate. This is same as KL divergence. Okay, optimizing all three of these kind of lead us to the same parameters theta. So let's start with cross entropy. No. So first, let's start with defining entropy. What entropy basically gives you is so first of all, like there is this whole entropy directly comes up from this another subject called information theory, and like to really get into the depth, you might need to read about all of the information theory, but just kind of introducing a small portion of it here. So what entropy tells you is, if I give you some data, what might be the most efficient way. Okay, so if you just Google it, then it would say something like, it tells you about the information content in your system. And what does that mean is, let's say I say that, uh, okay, yeah, so let's say I say something as, okay, today is 3rd April. So I think that is a bad example, but yeah, let's say I have two-headed coin, like a coin where both of the sides are head, and now I toss it and just I say that, okay, bro, uh, what I'm saying is, that the coin has ended lead, sorry, has landed head. So what is the information that you are getting out of it? It's basically nothing, right? Because the probability of that event happening was always going to be one. But now, what? Let's say if I am tossing a coin, that a two-sided coin with equal probability, and then I say, okay, now it has landed heads. Then there is some sort of information that I have provided to you. So so you can see that two similar statements might have different content of information depending on the distribution of where that information came from. So what Claude Shannon did was properly formalize this notion of this information content using this entropy. And so first I would just write down the formula. And yeah, given this, and this is just uh, summation over all the x's that you see. This is nothing but expectation of x over log 1 by dx. So what this formula tells you is, if x is distributed according to this probability distribution, what I would need is approximately this much amount of bits to encode the information in x. So if yeah, so this there is this awesome video of Khan Academy on YouTube about this entropy. So I'm if I give you an example of that. So let's say if I have four events A, B, C, D that are equally likely. This is system one, and this is system two. But now in system two, this is how my yeah. So seeing A, here all of them are equally likely, and here yeah. So this is how frequently I would see A, and this is how frequently I would see B, C, and D. Now, what you need to do is provide a best encoding scheme that can efficiently represent my data with the least amount of bits that I use. So what here I can do is simply give all of them equal weightage, and yeah, so just provide 2 bits to represent each of them, and I would be efficiently able to do it. But if I do the same here, then okay, so now this is kind of an exercise that you can try. Can can you provide a more efficient scheme than simply giving all of them 2 bits when you are encoding the information? So first of all, is it clear what we are trying to solve here? Is the problem clear first of all? And I would take these pauses just to ensure that you are all with me and I'm not just yeah, blabbering. Hello, someone.
Yeah, problem is clear. Like we are still thinking about this representation in
Yeah.
efficient way.
So one most important thing that you need to see that okay, since here all of these are each of these events is equally likely, so giving them equal amount of bits would make sense. But now I know that the probability of seeing A is twice high as the highest probability of seeing B. So the most efficient way would be to give least amount of bits to probability of A. Then that would be 0. And then but at the same time so if you look about information theory, you also need to ensure that whatever encoding scheme that you provided, you should also be able to decode from it. So I can't just provide each of them 0. So while I'm using the least amount of bits, but I am providing no information whatsoever. If it's just given this string, you won't be able to guess uh, what the original string was. So yeah, so an efficient way to do this is you just 1 bit to A, 2 bits to B, and 3 bits to C and D. It would be something like 0, 1, 0, 1, 1, 0, and 1, 1. So and now if you see that how much bits I'm using to represent system A, it's just 1 by 4 times 2, 1 by 4 times 2. Okay, it's 4 times 1 by 4 times 2, and this is just 2. Whereas in this system, I'm using half times 1 plus 1 by 4 times 2 plus 1 by 8 times 3 plus 1 by 8 times 3. This is half plus 3 by 4, which is 1.75. So in system 2, what I'm basically saying is I can represent the same information. No, not the same information. Uh, but yeah, so in system 2, I can because these probabilities of each of this events is unequal, I can represent it using less number of bits than this system. So and what simply this says is that whenever I say in this okay, event A has occurred, then the information that I provided to you is more when I say in this system event A has occurred. Because here event A was 1 by 4 times likely, whereas here, yeah, event A was, yeah. So it's an intuitive example of that would be saying that, yeah, if you follow football, then saying that some Barcelona has less information than saying Arsenal has won. So because it's yeah, Barcelona has more chances of winning than probability of Arsenal. So uh, so yeah, so if you see what we are doing here simply is just say if the probability of event is p of x, then what we need is log of 1 by p of x bits to encode it. Uh, yeah, and so it might be trivial to see here, but if you want formal definition, then Uh, I can provide some links about it, or you can Google it on your own. Like a formal proper definition on. So here it's clear, right? Like if the number of bits that I would need here would be since it's 1/8, it's log of 1/1/8 is log of 8, which is 3. But and here similarly here if it's equally likely, if it's 1/4, then log of 1/1/4, which is log 4, which is 2. These are the number of bits that I need uh, to represent an event that has probability of p of x. And given a data stream, this x is only likely p of is only going to come p of x times. So if I give you all of this data points, then this would be p of x times log of 1/p of x. And so th- this is how much bits I would need for one event, and a summation over all the possible xi's would provide me the entropy of the system. So that's basically what we have done here, is get the p of x, then get the number of bits. This is p of x, and this is log of 1 of p of x, and then sum over all the possible values that are possible. Is a definition of entropy clear? If you don't want to unmute, you can just give the thumbs up. Yeah. Okay. Nice.
Feel like I had just a doubt, no, not a doubt, but like, is this way of thinking about entropy correct? Like, in a way, matlab, like, we are being a bit more sure about the confidence of like how likely each class is in a way, kind of. Or means like, let's say if we have like higher probability, then it's like that chances are like that class will occur more often. Like, and if we have low probability, then like the chances are like that class is not going to be occurring. Right? Is it in that sense like proper way to think, or like is it more of like this way only? Like, it's,
Yeah. So let me understand what you are saying is correct. That if I tell you that some event has occurred, which has very high probability of happening, then the information that I provided to you is comparatively low. Like it's similar to saying, if I say okay, tomorrow an earthquake is going to happen in India. So the information that I have provided to you is very large compared to say that tomorrow no earthquake is going to happen in India, because the probability of earthquake not happening is very likely. So, so now you can see why it's inversely proportional to the probability, right? Where so in that sense, yeah, you are correct. Then that's how it's related to the probability.
means like you are more sure when you are just like basically saying the exact fact in a way, and if you are
Yeah,
not like basically sure, then you are basically kind of giving more diverse information, like this might be the cases like in a way, but maybe like sort of.
yeah, correct. So and yeah, so that is about entropy. That's all I wanted to say. Now, uh, second thing, that cross entropy. So sometimes what generally would happen is you won't have this probability distribution of p of x given to you beforehand. And yeah, so this thing, the formal symbol is h of p. And this is just, I'm just skipping uh, p of x. P just indicates the probability of an event. And yeah, and now what cross P is a distribution. And now sometimes we won't have this distribution P given to us beforehand. So what we would do is assume some distribution on that, uh, and let's say my assumption is Q. Now, because I'm not given this information P beforehand, the way I am encoding my bits is using Q, like assuming that I have a distribution Q. So I would encode each bit according to log of 1 by Q. But now the probability of that this okay, so let's say Q of X. So this much bits I need to encode this X, but still Q of X is not the correct representation of how X is distributed. The probability of seeing X in my data stream is still P of X. And this is where basically cross entropy comes in, where you don't know P of X, so you define it using Q of X, which is not correct. And so this H of P of Q is just defined as summation of P log of 1 by Q. This is how this much number of bits you are going to use to represent some event, but the probability of that event happening is still P. So you won't be able to calculate it because you don't have this information about P. But yeah, so uh, empirically, these are the number of bits that you are going to use. So that's cross entropy makes sense. And so this is just so I'm just rewriting these boots of h of p. X is coming from p of x log of 1 of p of x and h of p and q. This expectation of x is still coming from p of x. So log of 1 of okay. Is entropy and cross entropy clear? Okay, nice. So now one thing you should notice is that this log of 1 by p of x is the most optimal encoding that you can get of your system. So any other distribution that you do, log of 1 of q of x, you are always going to get so basically h of p of q is always going to be greater than h of p. And this is like, yeah, because and why this is the most optimal encoding is, as I said, you would look into the entire literature on information theory for that. But that's what Lord Shannon basically proved, that I when I said I am using this much number of bits, in no way I can use lesser number of bits than this when this is my distribution. Uh, when I need to ensure that I can yeah, I can convey this information effectively. And when I say I can convey this information effectively is after encoding I should also be able to decode it. And now so if we go ahead and minimize this, what you are basically doing is driving q near p, because so if you are changing q, you are changing q, and you want to be as small as possible. So now what you are doing is changing your estimate based on how less the information you need. And then So basically, what you are arriving, so you are not going to be less than this thing, and in order to so the smallest value of this is, as I said, h of p. So you are driving. If you are changing your q, then you are driving it towards p. So is this sort of, so if I'm optimizing this for I'm not writing the minimum or okay. If I'm minimizing this with respect to q, h of p of q, what I would arrive is make q closer to p. So is this making sense? And if I'm minimizing this quantity, then I can just add in any constant, right? Plus c minus c that is independent of q. Then this would be minimizing q h of p comma q. What I'm basically doing is now minus h of p. So these and these are equivalent because this is independent of q, and h of q p comma q is cross entropy between p comma q, and I can write it as summation of p log 1 by q minus summation of p log 1 by p. Then this becomes summation of p log of 1 by q minus log of 1 by p. And this becomes summation of p log p of q. This is nothing but KL divergence between p and q. Yeah. Did you get this? And now, as I said, that because of this, so this is also one of the interesting ways to prove why KL divergence is always greater than zero. We can also prove it using Jensen's inequality, but it also comes directly from the information theory. That because this h of p is the most optimal encoding, if you take the difference of these two, you would come uh, come at the KL divergence. So now, and you can see why these what KL divergence. So are you all familiar with KL divergence? And please feel free to unmute and say. If not, then I can give you a refresher on KL divergence.
Yeah, I think it'll be good if you just a brief at least.
Yeah. So KL divergence is one of the what the divergence gives you is basically quantifying how two distributions are close to each other, and KL divergence is like one of the if you were in the research like the ones taken by Akash, then even he said a bit about KL divergence and all of the literature on GANs and yeah. So most of these like all the GANs model variational encoders and come from this nation. Even in the future when we'll see EM algorithm, what we'll be basically doing is trying to minimize this KL divergence. What KL divergence says is now if I say you have this probability distribution and the other one is this, and at the same time I have this distribution. Now I need to quantify uh, which distribution is closer. This is P and this is P. This is Q1 and this is Q2. So I need to know out of Q1 and Q2 which distribution is closer to my original distribution P. And so KL divergence is an excellent quantity that would give you that. So, the way KL divergence is defined is it's actually so this is like we are coming from the other side of how KL divergence is defined. And now, wherever I have used summation, please use integration when you're dealing with continuous distributions. So it would be just p of x divided by q of x. And if p of x was continuous, then this would be so. This basically tells you how much closer q is to p. Uh, and like, let's say if q of x was exactly p of x, then this would be 1, and integrate p of x into 0, d of x would be 0. So yeah, so if p was exactly q, then KL divergence would be 0. And so the more farther p and q are, the more apart, the more different they are, the higher the KL divergence would be. So and this is nothing but log of p of x minus log of q of x. Expectation of this over x and x comes from p. So p of x is your true distribution from where x is coming from, and q of x is the distribution that you are trying to approximate. So if you are minimizing the KL divergence, again, what you are doing is driving q of x closer to p of x, because the KL divergence is minimum when q of x is 0. And you can also prove this using Jensen's inequality, that KL divergence is always greater than 0. So if you are trying to minimize it, you are trying to bring KL divergence to 0, and the only solution for when KL divergence is 0 for q is p of x. So you are driving your distribution closer to p of x. And these kind of optimizations are called functional optimizations, where uh, in normal calculus, what you are trying to optimize is a variable, but now you are saying you are trying to optimize a probability distribution, which is a function. So yeah, so what you are doing is driving some function near to an optimum point. So does that give you some idea about KL divergence?
Yes. Yes. Thank you.
Yeah. So mm, yeah, yeah. So so now you can see why minimizing cross entropy is the same as minimizing the KL divergence. And in both the situations, what you are essentially doing is driving q near p. Q is some probability distribution, your approximate probability distribution, and p is your true inherent distribution. And what you need to do is drive q near p in both of these optimizations. So at least I showed you this part, why cross entropy and KL divergence are equal. So any doubt in entropy, cross entropy, KL divergence, and why both of them are the same?
Intuitively, how can we interpret entropy? So, is it the number of bits that are required to calculate encode some information, or is it just the information?
Yeah, so exactly. So it's so both of them are kind of the same. So the information that I provide to you is dependent on how much. That's what how Shannon defined it. The information, the content of the information, if you want to mathematically measure it, that how much information that I provided to you, is you can define that by the most optimal encoding of how I would be able to uh, encode that information. So like
Yeah.
the number of bits that I would require in order to give you all of those information, so that you can kind of decode from it. So and that basically all of these three things, entropy, information, and number of bits required, are kind of the same.
Okay. So when we say that we are trying to minimize the cross entropy,
Hmm.
um,
So when you are trying to minimize this quantity, so in the terms of information theory, what this quantity is telling you is how much so I don't know the true distribution of my system P of X.
Yeah, yeah, yeah.
I'm estimating it with Q of X, and then now
I want to minimize the difference between those two things.
yeah. So, this quantity says you how much bits that you would require when your distribution is Q of X, and now you are minimizing that. So
Yeah.
what you are essentially doing is you are you want to fit in as much as information as possible in the least amount of bits required, and and what Shannon has provided is the lower bound that you cannot do less than log of 1 by p of x.
Hmm. Okay.
So you are, and hence invariably you are driving closer, you are driving q of x closer to p of x when you are minimizing cross entropy. And both of these things are same: minimizing cross entropy and minimizing KL divergence. KL divergence is like a formal notion of giving the difference between two distributions. And yeah, entropy and cross entropy comes from the information theory.
Okay. Thank you.
And
If real divergence and cross entropy is same, then why people use this name interchangeably, or why they have two names?
yeah, so because cross entropy comes from so so again, cross entropy is not the same as KL divergence. Minimizing cross entropy is same as minimizing KL divergences. And because formally, what is KL divergence between P and Q is nothing but the difference of cross entropy minus entropy. So this is true. This is always going to be true. And now, if I'm minimizing this, then because I'm minimizing it with respect to Q, this thing doesn't matter, the entropy of P. So minimizing KL divergence is the same as minimizing uh, cross entropy. And because both of these things are coming from different domains, right? Cross entropy and entropy are coming from information theory, whereas divergences and all is coming from where you are like quantifying how these two distributions, where you are explicitly quantifying how these two distributions are different from each other. So that's why you have two different names, and many people will directly start with KL divergences, and so again, KL divergence was not like a kind of a derived from entropy and cross entropy. This is like a separate notion completely, but essentially both of these come out to be same. So you can directly just start with defining KL divergences and how these two and how basically saying that these it defines how two distributions are different from each other and arrive at the same thing, uh, that in order to optimize Q of X, you are driving it to P of X, and which is completely valid. And probably might be that this is how it was discovered, and then the connection between the two was made. But yeah, so and now I would like to relate all of both yeah, any other doubts, and all of these are very good questions, and yeah, it's yeah, you need to clear all of it right away. So any other questions? Okay, I'm assuming not. So now again back to our original objective of maximum likelihood. Now, so I would also like to would love to relate it to machine learning. And yeah, and if you can notice this, this one thing I had to mention. Mhm. Okay, see here, if h of p of q, I'm defining it to be summation of p of x log of 1 of q by x. And now let's say I'm having just a binomial distribution that is x can take only two values. Mm. And then this would be okay. First of all, this is equivalent to this, and so P of X is my two distribution, right? So and Q of X is what I'm estimating, and now let's say this can only take two. Yeah, it's basically a binomial distribution. X can be either 0 or 1. This would then become negative of P of X. And now when I'm writing P of X, assume it's P of X is equals to 1 log of Q of X plus 1 minus P of X. And this is P of X is equals to 0 log of 1 minus Q. And again, this is Q of X is equals to 0. Now can you see the similarities between this cross entropy term and the machine learning formula that we use while minimizing while minimizing the classification, minimizing the loss, cross entropy loss in classification. So and okay, and now this P of X is equals to 1 is nothing but your while doing classification is nothing but your Y, and your output of the model is basically uh, for classification again. It's just going to be the probability of that like let's say I'm doing a cat classification model, and the output of my entire neural network is going to be uh, the probability of that I saw a cat, which is log of which is just y hat. And then this becomes y hat. Yeah. And so you are basically nothing but minimizing. This is how it relates to cross entropy. Uh, why the name cross entropy came while minimizing this objective function. Is this clear? Thumbs up, please. Yeah, thank you. So, yeah. Now again back to maximum likelihood estimate. So, and now this is how it's like for binary classification, but for generic multi-class classification, what your network would output is any neural network. And let's say we are having 3 classes, then it would output probability of X is equals to 1, probability of 0, 1, and probability of X is equals to 2. This is what it's basically outputting your neural network for each class. Yeah, each node would represent the probability of seeing that corresponding class. So what you are essentially doing is you are making a neural network learn a probability distribution over the classes, and P of 0, P of 1, P of 2. And this is the probability distribution that the model has learned, let's say. And this is Q0, Q1. So now I'm showing you how in even in machine learning, what you're basically doing is driving some probability distribution closer to its true form. So so in multi-class classification and like binary classification, a subset of this, what your entire machine learning model may be convolutional network or a normal artificial neural network, yeah, anything. It is just learning this probability distribution. And when I say probability distribution, one needs to ensure that Q0 plus Q1 plus Q2 and everything, all of these values sum up to 1. and that's why we like in the last layer we use this softmax function, which which essentially forces this constraint by normalizing all of the inputs. So yeah, I'm assuming you got that, but if you didn't, yeah, please tell me now. So I maybe I'll revisit what softmax function is and how that would ensure that each of these values sum up to one. Just feel free to unmute if you want me to go through that part. Okay. So I'm assuming everyone is aware of softmax and everyone is sure that all of these values would sum up to one. So what you got is proper probability distribution of over all the classes, and so let's say if you got this distribution, then what would be the likelihood of yeah so and now we also have this training set, right? So what would be the likelihood of this data after you now let's say your machine learning model has learned this distribution and now you need to evaluate it. So in machine learning, and the formula that we use is comes directly from this maximum likelihood estimate, where now you are seeing, given this probability distribution, how likely it is to see your the data that you are provided. And the data that you would be provided would be just with some samples of uh, mm, okay. So for each classes, let's say the true distribution comes from P0, P1, and P2, and you are provided n samples. So you are provided n samples of data, and this is the true distribution of each of the class. So for when x is equals to 0, the likelihood would be q of 0 times n of p of 0. So p of 0 is the probability that probability of class 0, and np of 0 is total number of samples that came from class 0. And this is the probability of you seeing how much you estimated it. And then again product of np1 and np2. This tells you the likelihood of your data when we are only dealing with three classes. But in general, that would be, let's say, C classes, then the probability would be Q of C times N of P of C. Another total number of samples, and P of C is the true probability of that class. Is this clear? Any questions for Ilya?
How did you, so the product that you have written Q0 raised to NP0,
Hmm.
what is this? This is the likelihood of our samples going into the zeroth class.
Yeah. So for the entire what this would indicate is there are n samples, and the true probability of class 0 is p of 0. So if I provided you n samples, then the total number of samples that would go in class 0 would be n of p of 0, n times p of 0. And you have provided me an estimate, a distribution that says that going in class 0 takes q of 0 probability. So then so if I'm going to see that np0 this np times, then so this likelihood, so it's like as
Product, yeah. Yeah.
it should be over n samples, and out of these n samples, np0 would go in 0, np1 would go in 1, and np2 would go in. So now, and this was for three classes, but now let's say you have C classes, then this is the likelihood of your data is, oh, oops, okay. the product of all these values. And now in order to do and now you need to maximize this quantity with respect to this QC value. Maximize over Q. And let's say yeah, so what we can do is directly do a gradient descent on all this. So this is but as I mentioned in the last class, this is same as optimizing this is same as optimizing x is same as optimizing log of x. And now instead of likelihood of data, we would generally want to deal with log likelihood of data because yeah, because optimizing likelihood is same as optimizing log likelihood, and log likelihood is quite easier to deal with because this product now, if I take this log of this product, then this directly becomes summation log of QC and PC. So now what we are interested in doing is maximizing over Q summation of log of QC. Okay, this is number of classes in this series. Just a minute. And this is called log likelihood. So then this becomes maximizing over Q is equals to 1 for total number of classes n times PC. You are maximizing over Q, so we can just discard n. PC log QC. And now I want to turn this maximization into minimization problem. So I will just multiply it with minus sign. Then this becomes negative log likelihood. Started with likelihood, then we went to log likelihood, and then we went to negative log likelihood. Minimizing this quantity, so I'm moving minus here, and then this just becomes this, and this is nothing but cross entropy. So yeah, any doubts still here? So what we basically have shown now is maximizing likelihood is same as maximizing log likelihood, which is same as minimizing negative log likelihood, which is same as minimizing cross entropy, which is same as minimizing KR divergence. All of these things are same. Yep. So, any doubts still here? So, yeah. So I think this would also be a good time to take a break, go through everything that we did.
I've got a question.
Yeah.
When we started off, we started with the likelihood as probability of y train given x train comma theta. That was our likelihood, right?
Yeah.
So
Yeah.
that
So yeah, that's a good question. So this so what we are here doing is when I said that get the take the likelihood as the points that you see in the data points that are given to you, the likelihood is just uh, multiplying all of the probabilities of that. And here, y train is kind of your output class. So given probability of so okay. So yeah, if I'm relating it to here, so choosing this Q0 and P0 gave me my probability of y train is equals to 0. Now x train is NP0 that's given to you, and Q0 and Q0 is your theta. So for categorical distributions, uh, the parameters of distribution. So if for let's say binomial distribution, the okay, anyone, yeah, tell me what are the parameters of binomial distribution.
So it would be the probability of success and the number of trial.
Yeah, perfect. P and N.
Yeah.
So P is the probability of success and another number of trials. And now in my so this N is kind of number of trials is kind of given to me. What I need is to optimize for this P. So here our P is Q because so both of these are binomial distributions. The true distribution is also binomial, and our estimated is also binomial, and N is the same for both of them, and we need to make our Q closer to P. So yeah, so here our parameter theta is nothing but this Q0, and yeah, N and P and Y are the number of Y is the probability of the data that you want to estimate your likelihood on. So given all of these, given these Y, what is the probability of me seeing those Y based on my model? If you carefully dissect the statement, I am given these kind of samples, which are of class for class 0, it's NP0 samples, which are my Y. Now, what is the probability of my model? My model says me that Q0 is the probability of seeing all of those samples, which is Q0 raised to NP0. So, so that's where this likelihood and this relates to that, where if mm, yeah, so here I would say this. So if what I'm trying to is maximize this, and now x train and theta is for me theta is this Q0, which I'm trying to maximize over. For I'm just considering single class, but now if you're considering all the class at once, then theta would be all of those Qs, uh, a vector basically Q0, Q1, Q2, and then X train would be so X train, but you would be provided the data in kind of pairs X train, Y train, and the Y train would correspond to which class the data corresponds to. So we are kind of dealing with categorical distribution. So Y train would be a multi class, and so while dealing with Q0, your Y train would be 0. So the probability of seeing number of samples in the 0th class would come out to be Q0 and P0. And since all of these classes are also independent, you would just take a product of all. So, yeah, can you relate this to what we did here now?
Yeah, it makes sense for the categorical classes. But what if we're doing classification? Sorry, it makes sense for classification, but what if we're doing regression? Because at that time, the parameters mean and variance, right? I think you wrote somewhere.
Yeah,
And
yeah.
then
But
how you
we are relating it to cross entropy. So in regression, we also don't use cross entropy loss, right?
Yeah, that's right. Yeah, but we can still for regression we can still use that likelihood function, right? That y train given x train and theta, but we won't relate it to the cross entropy.
Yeah, correct. So I would like to give that kind of that as an Even some mentioned that you should try it out. This so okay, this is not, not some kind of homework, but yeah, feel free to do this on your in your free time. So I've given you x train and y train. So let's say these are the data points x1, x2, x and yn. Now do a maximum likelihood estimate on these parameters fitting a normal distribution. So let's say new. Uh, yeah, let's just consider a univariate case. So maximize over nu and sigma square the probability of you seeing this. Let's say this is xd data points, xd over nu and sigma square. So yeah, fine. Yeah. So in your free time, go and do. So it's simple, and what you would see is that what nu comes out to be is just summation of xi over n, and what sigma square comes out to be is x minus xi. So, just a standard deviation of all of these values. Yeah. So, so this is the result. But what you need to do is just simply write the formula. Uh, since this is a univariate case, uh, and then just differentiate it with respect to nu and sigma, and then yeah, you would basically arrive at this quantity. And it makes sense, right? Like if I've given you these data points, then and I'm saying you fit the best normal distribution to it, then the parameters of the normal distribution, so that's why they come from the mean and standard deviation, and that's why we call it the mean and standard deviation. This is why this is called the mean, and this is why this is called the standard deviation, because these are the optimal results given those data points. So
Yeah,
yeah,
that makes sense. Yeah. So we just need to differentiate it, and then we have to equate this to 0 to find the maximum value, right?
yeah, correct.
Okay, got it. Yeah.
And so yeah, for such cases you directly get a closed form solution. And if you yeah if you have like a good amount of knowledge of matrix calculus, then you should also try this with respect to in multivariate case, when now nu would be a vector, and this would change to determinant of this. This would be 2 pi raised to k, and yeah, so x minus nu t sigma inverse and x minus mu, and exponent of minus r. So yeah, you should go ahead and also like differentiate this with respect to uh, a vector, and for in order to get the covariance matrix, you would see all the problems that you would face while differentiating with respect to covariance matrix. And now you also need to ensure that this covariance matrix is positive, semi-definite, and symmetric. So one simplification that you can do is here, just define that this covariance matrix is sigma square I. So all the diagonals are constant, and then find this optimal value for sigma square, and then you would again end up at this point. So yeah, so let's take a 2 to 5 minute break. Go yeah, and ask any doubt that you might have. Any general doubt, like in the previous lecture, or like while doing the Bayesian course you had, or in today's lecture, or something tangential to it that you have read and that you have any doubts regarding that. And this comes a lot. So I hope you are clear with all of these quantities: likelihood, log likelihood, negative log likelihood, cross entropy, and Kerr divergences. And that's why these simple formula that we use in all of our classification and all of the multi-class classification and dot cross entropy laws, all of these stems from this theory. So I'm assuming no doubts, everything was clear. So now that's all about maximum likelihood estimate that I wanted to say. So I hope everyone is clear on that. The only thing that we focused on was this part, that seeing your likelihood of your data. And so in all of these, we didn't assume anything that we wanted to. Uh, so our parameters theta, we didn't assume any prior distribution on that. So and in most of the cases, so in most of the cases, you might have some information about that prior distribution, and so and you would want to take that into account. So maximum likelihood, the major distinction between maximum likelihood and MAP is in MLE you assume a uniform distribution on your prior, where you just assume that I don't care about my theta. Like, I care about my theta, but I don't care about the prior distribution. I would just assume it that all of the theta that can arise are equally likely. So and now what we would do is kind of assume that okay, the theta that I have some kind of information about it. I yeah. So, and I want to incorporate that as well into my estimate. So in okay yeah, MLE estimate was just maximizing theta over p of y train given x train and theta, and now MAP estimate is maximizing over theta the same quantity, but now we have this additional theta that we are incorporating, and that was always there in the full inference, right? Probability of theta was always there, but in just MLE we assumed, because we didn't have any information, we just assumed it was uniform. But now we are explicitly stating that we have some information about it. And now, can anyone of you tell me the linear regression that we did earlier in the first lecture was the weights that we obtained? Was that an MLE estimate? Was that an MAP estimate? Or was that the full Bayesian inference estimate?
I think that was a map because we did took prior into account.
Yeah, exactly. So in the first example that I provided, what we did was assumed that probability of uh, theta was normal, yeah, so this is theta centered around zero with some variance square. And this is what we took into account. And we could have always said that, okay, this was just one. And if you remember the proof, what we ended up was minimizing theta with respect to y minus theta x the whole square. So if we had just assumed that it was a uniform distribution, then we would have ended up here. But because we also assumed that this was a normal distribution, we incorporated our own beliefs about what the weight vector should be, and what we needed was the weight vector to be as close as possible. So we also got this lambda term, which was yeah. And even as they posted some question in the quiz, you can also assume some another distribution on these parameters, and then you would have gotten something else. I don't remember the distribution. I think it was common. I'm not sure, but what you would have ended up was getting this. So
It was Laplace distribution.
yeah, so if instead of this normal distribution, you would have used a Laplace distribution, then you would have got this would have been replaced by this. So uh, if you want to relate it to all the machine learning that you have been doing, what MLE estimate would just give you a loss function, and if you want to incorporate this map estimate, then it would also kind of give you a regularizer of some sort. Uh, so yeah, and that's what we have been doing in machine learning. So this comes from MLE estimate, but if you want to, and this entire thing comes from a map estimate. Now, because in machine learning, what we told was saying that weight should be as small, that giving penalty to weights that are farther away from zero is same as like you are incorporating some prior knowledge about the weights in your model, and and that prior knowledge is comes in the form of the distribution. So and that's how you would find a map estimate now, where you would have a theta as well, and then if you want to do a full Bayesian inference, as discussed last time, which is a very hard problem, then what you would need is, yeah, even this quantity as well. And getting y train given x train, yeah, in order to obtain this, what you would kind of need to do is probability of uh, full Bayesian inference d theta. You have to kind of solve for this, and again, this single integral looks deceptive, but your parameters theta are not never just a single univariate variable. It might be uh, so if you have some neural network that has 1,000 parameters, which is comparatively very small model, but then there would be 1,000 integrals stacked together. Yeah. That's why obtaining this is, yeah, if you go it in the integral way and you sit down and you cannot just sit down and integrate it. You either need a direct solution for this, or yeah, so in some cases you might be able to directly obtain uh, closed form solution of this integral directly, but yeah, in most of the cases for our neural networks, or yeah, for our neural networks where the function writing the function itself is tedious, doing this integral is, yeah, is impossible right now. So for those neural networks, obtaining this is kind of hard in order to do this full Bayesian inference, but choosing distributions in such a way that we can sometimes get this closed form solution, and we might be able to do this. Yeah, and so the one thing that I wanted to say is, after MLE, you would get a point estimate again. After MAP, you would also get a point estimate, because in both of these, you would see that what you're doing is just doing a maximization over this theta, and it won't just be point estimate, but that point estimate would be the mode of your distribution. So mode of distribution over theta, and MLE is just MAP with uniform prior. But doing a full Bayesian inference, you are also obtaining this. Yeah, somehow you would be getting this value, and then the thing that you are obtaining is directly a full inference. You are getting a probability distribution over theta, given x10 and y10. So any doubts between MLE, MEP, and full Bayesian inference. So we would go through one example of all the three to hit it home, but theoretically, uh, you see the difference, right? Any doubts? So if everyone can just give a thumbs up, you understand it. Okay. All right. So in a perfect world, we would always want this do a full Bayesian inference and just choose the parameter according to our convenience. The parameter might be the mode. Sorry, the parameter might be the mode or the mean or any sort of quantity that we might be interested in. But it's only possible for us to do MLE and MEP, which all of our general machine learning models do, and we are only left with a single point estimate. But yeah, and one more point that I needed to tell about MEP. So after this, after multiplying this, what you generally, yeah, so it's again this distribution on theta, right? So in this given this theta, you are getting this new distribution on the same theta, but now you have observed this X train and Y train data. Yeah. So now you have this. So you in MEP, as I said, we are only concerned with the numerator. This denominator is independent of the theta. The theta you observe are only in the numerator, and the output distribution that you get is also on the same variables theta. But uh, this theta is your prior knowledge where you didn't see any of the data. Uh, Without seeing data, something that you observe, like without knowing my x's and y's, I just want to ensure that all the weights are as small as possible. So, and in that sense, we used a normal prior centered around zero. But now, after seeing this data, what is my updated distribution? So, so what you would want ideally is the distribution itself shouldn't change. Only the parameters should change because the distribution is over the same variable, same random variable theta. The only thing that changes you have observed some data. So, and that's why the idea of conjugate distributions comes in. This is right information. Yeah, and what conjugate distribution says is yeah that if this is let's say a probability distribution PA, this is PA with parameters x. Okay, if this is a probability distribution PA and this is a probability distribution PB, after I multiply that, the new thing that I get should also belong to the same family with SPB. The parameters of the distribution can change, but the distribution itself shouldn't change. So, an example, if let's say if I assume this is some uniform distribution and this is some normal distribution, then my output is a normal distribution. This is not conjugate because the distribution itself changed after multiplying these two quantities. Generally, what we would ideally want is distribution, and this also helps in sometimes obtaining a closed form solution because you can take this as probability of y train given x train comma theta and probability of theta d theta. I'm just using a Bayesian theorem here. And then what I want to ensure is the product of these two distributions, y train given x train and theta, should be a family of probability of theta. So I'm not saying these two should be same, but let's say this distribution is parameterized by A, comma B. This can be parameterized by C, comma D. But if I started with a beta distribution, then this should be also beta distribution. The parameters can change, but the distribution itself shouldn't change. And if such pairs are called the conjugate pairs, where multiplying those two distributions would not change the distribution of AB. So first, did everyone understand why we need conjugate distributions? And second, what are conjugate distributions? Thumbs up, please. So no doubts. Yeah. So and so sometimes in order to get a closed form solution, conjugate distribution helps us a lot. And conjugate distribution ensures that this distribution of theta doesn't change after seeing some data, which you wouldn't want. So some examples of conjugate distributions are, first, let's say P of theta is normal with some, mm, yeah, okay, mean is x, okay, mean is m, and standard deviation is s square, variance is s square, and this is also a normal distribution. Hmm. Over the mean, so okay, so okay, so Anil, maybe you can help me out. The normal distribution here is conjugate only with respect to the mean, right? Not with the variance.
Normal distribution is conjugate with respect to the mean, not the variance. I wasn't following what you're saying. I'm sorry.
Yeah, okay. So wait, yeah.
So you place a normal prior and you're saying y train given x train is equal to then. Yeah, if all of those
yeah,
are normals, then the posterior will be a normal, yeah. Joint is a normal,
yeah, but
conditional is a normal, marginal is a normal.
yep, yeah, but it's defined over this different variables, and I think the standard deviation should be the same, right?
I
Because so I know that gamma distribution is conjugate to normal with respect to precision. Wait. So I would hold off on this example. Yeah. So if you multiply two normals, the output is always a normal. But here the thing that I'm worried about is if this is parameterized by theta, then there would be x minus theta sigma square here, whereas yep. Yeah, I guess this should make sense. So yeah, um, what we are doing here is this first distribution is a normal where theta is itself the parameter, uh, because yeah, y tin given x tin comma theta, and the second distribution is some random parameters a comma b over your parameters theta. So uh, so I hope you are getting here. This first distribution is here theta is a parameter, and in the second distribution there is some distribution over the parameter which has some additional parameters. So if theta comes from normal, uh, where this is the distribution over the variable, and these are the parameters. I'm saying mu comma sigma square, and now if I have this new distribution x, your theta is a parameter and there's this new variable as well. So now if I'm multiplying these two distributions, probability of x and probability of theta, x given theta and probability of theta, what I end up is in general, whenever you are dealing with multiplying two normal distributions, you only care about the exponent term because these are all just constants. So this would be 2 pi sigma square, and this would be 2 pi s square, and the exponents would just add up. So minus 1 to sigma square, and for x given theta, we would be x minus theta the whole square, and minus 1 to s square theta minus nu the whole square. So this is just a constant. And now what we are left with is two. Yeah, so let's say this is constant C1 and this is constant C2. And you can see that this, again, what you end up is getting a quadratic in theta. And now, since whenever the exponent is quadratic in some variable, you can define a normal distribution by just normalizing it. So the output is again some normal with theta, but now the parameters won't be nu and sigma, and that's it should be nu dash and sigma square dash, sigma dash the whole square. Okay, so did you understand why the normal is conjugate to each other on mean? Because this here theta I'm assumed to have take this as a mean. If I had taken this as some, let's say, mean and theta square, then this and this wouldn't be conjugate. You can try this, and you won't see a quadratic in theta because this theta would end up at the bottom. So yeah, did you understand this?
I've got a question. Here you say
Yeah.
that theta is a normal distribution, right? Where you said theta given mu and sigma square. So these are the two parameters. And then I can get it in the next line you wrote, we're using theta as the mean.
Yeah, so that's what we want in conjugate distributions, right? So our probability of x given theta and probability of theta, and this is what we are end up getting. So this is a normal Bayes theorem, and in conjugate distribution we want this and this. So theta is nothing but a parameter, and then you are assuming a prior on the distribution of theta. So yeah, in the example of normal, theta is nothing just but a parameter of x given theta, and this would be your theta as a weight vector. So if I'm relating it to the linear regression case, then theta would be a weight vector, and then now I'm assuming a distribution over the weights. So this and this are two different distributions, and this is my distribution on x, where theta is the the theta is the parameter, theta is the mean, and this is my prior. This is the prior on my parameter. Did you understand that? So normal is a conjugate to normal with respect to the mean.
Okay, I understand the first line, which is the prior. What's the second line? It's the likelihood.
Yeah, you can call this likelihood of you seeing your data. This
Right.
would be the margin.
And the parameter for your likelihood is going to be the theta from prior. Is that what you meant?
Yeah. Yeah, correct. So yeah, and similarly in linear regression case, this likelihood here we had just a function of theta instead of theta, and function of theta was theta x. And here there was this y, but yeah, so if I'm relating it to the linear regression, x would change to y, and this would be a function of theta x. Function of theta would be theta x. And then your theta would be this weight vector w, and this mu was just 0, and sigma square was just sigma square I. So conjugate distributions ensure that when you multiply probability of x given theta and probability of theta, and here theta are the parameters of your, this is the prior with, let's say, parameters a comma b. This is a new distribution that you get after seeing your x. So uh, this is what the generally the notation is, and I can see why this is confusing, because x here is not the x here is not the parameter of this distribution theta. X is just information that is given to you, and this notation is used in order to indicate that this is the information you have. But here theta is the information about the parameters, and here x is just the information that you got recently, and how based on this information you are updating the parameters. So what I would do is then this would be probability of a dash comma b dash of theta given x. So I hope this one makes more clear. Here a and b are the parameters of theta. Here theta is the parameter of x, and we want that after multiplying this, the distribution of theta in itself shouldn't change. And if a and b, if these two distributions are such that the distribution of theta doesn't change, we call them conjugate distributions. And a dash and b dash are the updated parameters of theta, but now we have the information after seeing x.
Yeah, I think this is make more
So
sense.
yeah, so now I was hoping to do an example of all the three MLE, MAP, and okay, another homework that you, I can give you is, but you can try this at your home, is gamma distribution is conjugate to normal with respect to precision. Now precision is nothing but 1 over sigma square. And now when I say with respect to something as in the parameters, so here I said it's with respect to the mean, because the parameters of the x I substituted. Yeah, so the parameter, the prior that I had was the mean of my distribution of my likelihood. So here the prior on gamma would become my, so if yeah, so theta would be a gamma distribution, and now 1 by theta, because now would be the variance in normal on x. So you can try to prove this at home. So yeah, I hope the question is clear. And so and so I had an example prepared. So okay, so let's say initially, as the first example, what I would want to do is, mm, mm, yeah. So let's say we okay. So let's say there is this football tournament that is going on. There is this team. Uh, mm, let's say Arsenal. I'm just trying to make this example as intuitive as possible. Won 30 on 38 matches. Now Arsenal is going to play some next match. So this is a tournament that's going on. Tournament. So Arsenal is going to play next match, and we need to predict the probability of Arsenal wins the match. And okay, simply what you would do is just calculate 30 on 38, which comes out to be 79%. Just only based on this information that we have, what we would do is yeah, take the ratio and just calculate this, because this is the only information that's available to us. Uh, Formally, what you would like to do is there are just two outcomes, and so we would define Bernoulli distribution. So let's say the probability of Bernoulli with not Bernoulli. Yeah, let's say we define a binomial distribution with n and p. P is the probability of Arsenal winning the match. And we know then p of x is okay. So probability that k out of n matches were won by Arsenal is nothing but n c k p of k 1 minus p n minus k. So so yeah, this is just binomial distribution stuff. And then so our distribution would be defined as, now your theta would be the p, and you need to calculate the probability of your distribution. Now of course it's going to come out just 30 by 38, but I wanted to do this formally. So this is nck k wins out of n, and we need to maximize this for theta. And so what we want to is okay, that our data has shown that it has won 30 out of 38 matches. Then n is 38, c is 30, theta is yeah, theta is what we want for, k is 30, and 1 minus theta is 38. Mhm. This should be n minus k, and this should be 8. So yeah, what we are simply saying is, okay, now we have this distribution over theta, and this is the only data that we have. What's the likelihood of seeing this data? So I have some distribution that I'm saying that Arsenal the probability of Arsenal winning is theta, which is the best theta that explains this. And that's going to come out 30 on 38 because it has won 30 out of 38 matches. But yeah, formally you would do it like this. So best theta that can maximize this. Winning 30 out of 38 matches, and theta is the probability of winning the match. So okay, theta is p, so I have just write your p, and we will maximize over p. So what we can just simply, this is a constant, we can just ignore it, and we can just yeah, differentiate it with respect to p. So using the product rule of probability, what we would end up getting is 30, 29, 1 minus p raised to 8 plus p raised to 30. So I hope no one has any doubt in this section. Then this I need to equate it to 0. So this becomes 30 p 29 is equals to p raised to 38 times 1 minus p raised to 7. So I can cancel this, and then I'm only left with this, and then I can cancel p raised to 29, and I would be only left with p. So 30 minus 30p is equals to 8p. 38p is equals to 30, and p is equals to 30. 38. Not surprising, but that is how you do find a maximum likelihood on this data. And now you have some information on uh, so the best distribution of the best estimate of your parameter p was 30 on 38. So yeah, so the distribution that you would get is binomial distribution with ps 30 on 38, probability of Arsenal winning a match. But now let's say I had I also want to incorporate some prior knowledge on this data, so that prior would be let's say that there has been some a previous tournament, and now you also have this information about Arsenal. Okay, in the previous tournament, Arsenal won 10 out of 15 matches. So you would also want to incorporate that in your estimate, and that can be done using anything. So mhm. Yep. So okay, and I think I've been using the term binomial here, but the only estimate that we wanted was on P, the probability of Arsenal winning a match. So it should be Bernoulli, because n is just given to us, and we just want P, the probability of something winning a match. And okay, so now MAP, we are interested in MAP estimate. And for MAP, one thing that you need to define is this another distribution. So this is the probability of x given theta. We have come up with that as a Bernoulli. And now, in order to decide which prior to select, we would need to, okay, I think people are dropping off for dinner. Should I stop here, or should I continue and they'll
I feel
revisit?
like pausing is important. We're also almost at time, so like 15
Mhm.
minutes before time, and it might help if you stop.
Yeah.
But
Okay.
complete the. I'm assuming you're going to talk a bit more about the example, like what you did. So
Yeah. So it might take time, but okay. But for map estimate, we would need to define a prior on this Bernoulli distribution, and the and in order to make that as a conjugate, what we would use is so these priors is something that like each distribution has a corresponding prior, and yeah, you can kind of prove it on your own, but beta distribution is prior to so it's also prior to binomial, but again, not on n, but on the value p. So binomial would be defined as n comma p, and Bernoulli just p. So binomial with respect to this parameter p, or just Bernoulli with respect to the parameter p. So y. So I'm assuming you are all familiar with beta distribution, and so this would be defined as some constant. Okay, can anyone tell me what this constant is?
It's some sort of
This
gamma,
would also,
if I remember.
yeah, yep. So this is gamma of a plus b times gamma of a gamma of b, and you you should go ahead and read about beta distribution if you are not familiar with it, and why this term came here, because if you integrate it out, you would just get 1 by beta of a by b, and beta of a by b is equivalent to inverse of this. This is a formula that you all should be aware of. And yeah, you should also read about the proof of this. Yeah, it's quite interesting. But yeah, so this is the constant. We are not worried about this constant because it's just a constant. And this is the prior on beta, and now you also and the likelihood is given by your Bernoulli distribution, which is just nck theta k 1 minus theta of n minus k. This is Bernoulli, which is probability of x given theta, and then prior is some constant theta of a minus 1 times 1 minus theta of b minus 1. This is probability of theta parameterized by a by b. So this is also. So if we multiply these and this, then we would end up with theta of k plus a minus 1, 1 minus theta n minus k plus b minus 1. So now you can see that this is also a Bernoulli distribution. This is some new constant. This constant is precisely a plus b. Yeah. So this okay, this I'm sorry, this should be I guess just yeah. And so yeah, and you can see that this is just a Bernoulli distribution on theta, but now you have the parameters updated. Now p is nothing. P is now k plus. Oh, sorry. P is just so now you have this parameter theta 1 minus theta, and now you have p remains the same, but now it's theta of a plus k n minus k. You can see that this distribution and this one has the same functional form. Just the value of k and n changed. K is now a plus k and n is k minus k plus k. So, I think I got confused with binomial and Bernoulli somewhere. So I think maybe now we'll go to the next lecture. In the next lecture, I'll clear this up. But now, at least I hope you can see that Bernoulli binomial is a like conjugate to beta distribution. And then in the next lecture, we would continue with this example, and then we would go on with and for this example where we have this Bernoulli binomial type distribution, we can do a full Bayesian inference easily. So I think I would stop here and I would take any doubts that you might have.
Right, I've got a question. So when you say when we're going to do full Bayesian, it means we're going to be calculating the evidence as well, right?
We would be calculating the denominator as well, yeah.
So that's what it means by full Bayesian, right?
Yeah. Whenever I say doing a full Bayesian inference, yeah, we are also interested in this denominator.
Right. Okay. So if I understood correctly, if we are using conjugate prior, then we don't have to calculate the evidence, right? Because it's kind of like make the whole equation easier, right?
It would make it easier for you to calculate the evidence, but you will always have to calculate the evidence. Like whenever you say we are doing full Bayesian, and so just when I say we are using conjugate distribution, we are saying that the product of this distribution lies in the same family of p of theta, and so we would use that property while doing this integration. Uh, so where did I mention that? Yep. So we would kind of split it up in this way, and then we would use that product of these two distributions would give us a distribution in the same family of P of theta, and then we would use that to do the full Bayesian inference, but we would always have to calculate this whenever we want the entire distribution of the data.
Right. Okay. So like for example, if we are calculating, like if we are just using MLE or MAP, we can still use a conjugate prior. Is that what you meant?
Yeah.
Right. Okay.
Yeah, we can always for ML it doesn't make sense because for ML we don't need a prior
Oh
on
yeah.
theta.
Yeah, that's right.
For MAP, yeah, always. For MAP, sometimes we would want to use a conjugate prior because we want that output distribution should also be of the same family. So it makes sense to use the conjugate prior
Right. Okay.
in MAP.
Makes sense. So when we're doing MAP and full Bayesian inference, it's better to use conjugate prior.
Yeah, so it's better in terms of to get a closed form solution and in order to perform your analysis on it. But sometimes it's not required for you to use that. So you can have some ulterior distribution on P of theta. Then this distribution would belong to some another family entirely, and then the whole process of inference becomes messy. But if you have those particular needs, then you can use that, but then you won't be able to do a full Bayesian inference that easily.
Right. Okay. So for example, if we didn't use conjugate prior, so we only have a closed form solution, right?
Yeah, so in most of the cases, like you would have to manually work out everything, and there is high possibility that you wouldn't get any closed form solution for that. And these kinds of these kind of needs would also be limited because generally whenever we want after seeing the data, the distribution on the parameters shouldn't change. So now if P of theta, like for our example, when initially we had a Bernoulli distribution, then after seeing some more data, it shouldn't be like some okay Poisson or some another distribution entirely. So that's why this kind of assumption makes sense, and it also simplifies all our calculations.
Right. Yeah, makes sense. Thank you.
Yeah, and any other doubts, any feedback?
I really like the use of the football example. That was nice.
Yeah, in terms of feedback, I think the session was great. So thanks for your time.